We're going to look at an example of a matrix that has complex eigenvalues. So let A be this 2 by 2 matrix, 1, 1, negative 1, 1, and let's find all the eigenvalues in the eigenspaces. So what's the first thing we need to do? Well, we need to find the matrix A minus lambda I, where I is the 2 by 2 identity matrix. Well, this is 1 minus lambda, 1, negative 1, 1 minus lambda. And then we need to take the determinant of this matrix. This is 1 minus lambda squared minus negative 1 times 1. So we get 1 minus lambda squared plus 1. And this determinant is the characteristic polynomial, p of lambda, which is equal to 1 minus lambda squared plus 1. Now I would like to write this characteristic polynomial in a factored form. So I would like lambda minus an eigenvalue, and if there's more than one, lambda minus first eigenvalue times lambda minus second eigenvalue, and so on. How can I do this? Well, I'm going to set this characteristic polynomial equal to 0. You could try to expand this, and you'll see that you get something that's not factorable over the real numbers. The only eigenvalues for this particular polynomial are indeed complex. So I'm not going to expand this, but you can do that and try to factor it if you want to, but you'll see it's not factorable over the real numbers. So I'm setting this thing equal to 0. I'm going to move the 1 to the other side. And then I'm going to take the square root of both sides. Remember, when you take the square root, you get a positive and a negative. And the square root of negative 1 is I. So I get that 1 minus lambda is equal to plus minus I. And I'm going to solve for lambda. So what I'm going to do is I'm going to move this lambda over. And I get 1 is equal to lambda plus or minus I. And this is two equations in one. You have 1 is equal to lambda plus I and 1 is equal to lambda minus I. And I'm going to move both of these i's to the other side, and I'm going to combine them into one equation. So I just get 1 plus or minus I is equal to lambda. So these are my two eigenvalues, 1 plus I and 1 minus I. So let's rewrite this equation. So this characteristic polynomial is equal to lambda minus 1 plus I times lambda minus 1 minus I. Now, something you can do if you want to double check, just to make sure that it's correct, you could FOIL all this out, and you should get the same polynomial. Another thing you can do, if you don't like all of these parentheses, you can go ahead and distribute this negative to everything inside those parentheses. And if you did that, you would just get lambda minus 1 minus I times lambda minus 1 plus I. So that's just another way to write the polynomial, the characteristic polynomial. But this one's easier to pull the eigenvalues from. Okay, since we know what our eigenvalues are, we need to find the eigenspaces. Also notice that the algebraic multiplicity of the eigenvalues is 1 because the powers on both of these factors is 1. So let's find the eigenspaces. I'm going to start with the 1 plus I eigenspace. So how do we find this eigenspace? Well, we need to find the null space of A minus 1 plus I times the identity matrix. That will be the 1 plus I eigenspace. So all I need to do is plug in 1 plus I into this matrix here. So I need to find the null space of the matrix 1 minus 1 plus I, 1, negative 1, 1 minus 1 plus I. Let's focus on this matrix here. If I distribute the negative, I just get a negative I, a negative 1, a 1, and a negative I. And what do I need to do here? To find the null space, I need to get this matrix in reduced row echelon form to start off with. And then I need to make it an augmented matrix and put a line and put 2 zeros and then solve for x1 and x2. Because remember that the null space of some matrix is a set of all x such that c times x is equal to 0. This matrix is a 2 by 2 matrix, so x is going to be x1, x2, and remember what we do. We put c here and then 2 zeros, and this is going to have 2 columns, and you'll be able to figure out what x1 and x2 are from the reduced row echelon form of c. So anyway, let's do that. Now there's several different things you can do. The first thing you can do is divide by negative I to make this a 1. That's fine. And then you'll have 1 over a negative I, and then you need to multiply the top and the bottom by I. You have to do a lot of work. I think what I'm going to do is I'm going to actually just multiply this row by a negative. So I get negative I, 1, 1I. And then from there, I'm going to multiply this row by I. Then I'm going to add it to this row to get rid of this negative I, and then I'm going to exchange the rows. So I'm going to take I times row 2 and add it to row 1. And to get here, I just took negative times row 2. Okay, and if I do that, I'm going to write it here. I get I, and I times I is a negative 1. Okay, so we're left with, if we add this, we get 0, 0, 1, and an I, just keeping this one here. Switch the rows. And you get 1, I, 0, 0. So now that we have our reduced row echelon form of the matrix, we put our 2 zeros here. Remember, this is x1 and x2. We get that x1 plus x2 is equal to 0, which tells me x1 is negative I x2. Choose one of these to be a free variable. Since I solved for x1, I'm going to let x2 be free. So then the null space, oops, got some writing over here. The null space of A minus 1 plus I times the identity matrix is a set of vectors that look like R negative I times R, where R is a complex number. So I'm just letting x2 equal R. And now we find a basis for the space. So this is just the span of negative I, 1. So we have found the 1 plus I eigenspace. It's just the span of this vector. And the geometric multiplicity of 1 plus I is 1 because that's the number of vectors you have in the basis. Great. Let's move that up. Oops, didn't mean to do that. Okay, let's copy this. I think that's what I'm going to do. Actually, I can just memorize it. So it's negative I1. So let me solve this. I hate that I don't have a lot of, I can't move back or erase things quickly. It's one bad thing about this program. Okay, so we said that we had lambda is equal to 1 plus or minus I. Those are our eigenvalues. And we said that the 1 plus I eigenspace is the span of this vector. It was negative I1. Okay, great. Let's find the eigenspace for 1 minus I. So that's what we're going to do. We're going to find the 1 minus I eigenspace, and it's going to be very similar to what we just did. So our matrix A minus lambda I was 1 minus lambda, 1, negative 1, 1 minus lambda. So wherever we see a lambda, we're going to put in 1 minus I. And we get 1 minus I, negative 1, 1, 1 minus I. So this time we get an I, not a negative I. And we're going to do the same thing we did last time, which was put this matrix into reduced row echelon form, and then find a basis for the null space of this matrix. Okay? So I1, negative 1 I, put it in reduced row echelon form. I'm going to multiply this by an I. So if I do that, I get a negative I, do it in red, negative I, and then a negative 1, and then I'm going to add it to the top. And I get 0, 0, negative 1 I. And then I'm going to exchange the two rows, and I'm going to make this a positive. So I get 1 minus I, 0, 0. And from here you can figure out what the null space is. The only difference between this matrix and the one we saw last time was that I have a negative I instead of a positive I. So then if we put 1 negative I, 0, 0, 0, 0, we get that x1 minus ix2 is 0, so x1 is ix2, so x2 is free. So the difference in the basis here is just that I have a positive instead of a negative I. So the null space, or the 1 minus I eigenspace, is just the span of this vector 1, I1. Because I'm letting x2 be r, and then I get I times r, and then you factor out the r. So you just get I1. Let's write that near the other eigenspace. Okay. So now we've found it, and it's equal to the span of I1.